Welcome back as we continue the Algebra 2 PLC around the Semester A exam review items. I'm James Key with the MCPS math team.
And I am John Chase. I'm a teacher at Richard Montgomery High School. So let's jump right in, and we're going to take a look at exam review problem 33A. In this problem, we're asked to solve an equation symbolically and then also discuss an extraneous solution. So let's do that. The solution should be somewhat familiar to us, so square both sides and go through the algebra. But the thing we want to highlight here is what I'm going to write off to the side here. And that's a discussion around what is the solution set at each stage. So at the end, it seems like x equals 2 and x equals negative 2 are our solutions. So, and certainly to this equation, those still satisfy this equation. But if we go back up and check in the original equation, we find that 2 works, but negative 2 doesn't work. And I think the question that students have, and that some of us might have too, is how did that happen? So in fact, let me start by writing the solution set up here. It seems that x equals 2 is the only viable solution. So somewhere along the way here, we lost a solution. So let's go from the bottom up. From down here, it's clear to me that if I plug in, and we can just do this mechanically like a computer, we can just plug in x equals 2 and negative 2 and see when it works and when it doesn't work. On this last one, it's pretty clear to me that both still work to this equation. It's certainly true that if I square either of those things, that it works. And I won't go through the math, but it works on this one here too. We can actually plug it in on the left-hand side and the right-hand side, and we will see that we get an equivalent expression. And same. Well, now I have to think about this. All right, now it's getting a little dicey. Is that right? So something happens when we square something, maybe, that we lose a solution. And I think we've had this discussion before on this PLC, but let's have it again. If a equals b and we square both sides, it's certainly true that we get an equivalent expression. A equals b. If a equals b, then a squared equals b squared. But we have some big question marks about the converse of this statement. This is 100% always valid, whereas this is an invalid, in general, an invalid.
So John, I'm just thinking about that last statement. If a squared is equal to b squared, what could happen besides a being equal to b?
Yeah, it's hard for us to use symbols to show our students. It's easiest to reach for an example, right? Suppose someone claims that 3 equals negative 3 because when squaring both sides, we get 9 equals 9. Well, this is certainly a true statement. All the while, this one being false. So I think that, even just a simple example like that shows forth the fact that this is false.
Absolutely. And just in thinking about the fact that, as you said, when a is equal to b, it's quite true that a squared and b squared are the same. Whereas if a squared and b squared are the same, the other alternative is that a is equal to the opposite of b. Mm-hmm. And you kind of exemplified that in showing what goes on with squaring 3 and negative 3, that their squares are equal, but the original numbers just aren't. So that's kind of an algebraic point of view around what goes on with this equation and the fact that there's an extraneous solution hanging out with us. However, in receiving this email around this question, I kind of have a feeling that the teacher might have wanted us to speak to the graphical component, so let's go ahead and have a look at that next. So in looking at the graphs of y equals this expression and y equals this expression, we see that those graphs meet at the point where x is 2 and y is 3. And that's telling us that the value of x that satisfies this equation is 2, because when we replace x with 2, the expression on the left and the expression on the right both have the same value, namely 3. So this is in fact the legitimate solution, as John pointed out in working through the equation symbolically. However, there's an item that asks students to show how the extraneous solution could be presented graphically, and how is that related to the actual solution and the graph that goes along with that. So in thinking about this, what I've written here is y3 is actually the opposite of this expression, okay? And just to link things up, we talked about how if a squared is equal to b squared, then a might be equal to b, or it might be equal to the opposite of b. So what I'm doing here is I'm just playing on that theme, letting y3 be equal to the opposite of this expression, and just kind of seeing what can happen. Well, when we take the opposite of that expression, we just get a reflection of the graph in the x-axis, and so that's what's shown with the dotted blue line here. And the other graph of the line is just the same. And those graphs meet at -2, -1. And what we find is that -2, -1 satisfies both of these conditions right here. And in fact, it satisfies this squared condition as well, since -1 squared is indeed equal to -1 squared. So x is -2 is a solution to this equation right here. I'll just call it equation B. All right, so this works with equation B. However, if we look back at equation A, the original equation whose solutions we're supposed to be describing, we're going to find that it doesn't work. And let me go ahead and just check that really quickly. So if x is -2, we get -2 plus 1, which is -1. Already I see there's a problem. We know that the range of the square root function does not include negative numbers, but let's just go ahead and see what happens. 2 times -2, -4, add 5. We get the statement, the square root of -1, which is just undefined, is equal to -1. Well, no, it's not. These are not the same. So again, this ordered pair satisfies the transformed equation, but not the original equation.
Yeah, sorry to edit there. We mean 1 squared on the last example. -1, 2 times -1 plus 5 is 2. What did we put in? -2 is a +1 under the radical.
Really good catch there.
Sorry about that, James.
Well, you caught me in a math error there. So 2 times -2 is -4, add 5 is indeed +1, and the square root of +1 is 1, which is not equal to -1. So the point remains the same, but thanks for catching me in a math mistake there. John, do you want to talk through the slide around 33C,
Sure,
where a different angle is presented on the graphical approach to the extraneous solution?
Sure, sure. The other thought that we could have is, around, again, I'll bring back the A's and B's for a little bit of a show again. Earlier we talked about the fact that if A is equal to B, then A squared equals B squared. But if A squared equals B squared, then either A equals B or A equals -B, or -A equals B. We could say it either way. And so in this picture we have that other interpretation. We have that what happens if we negate this side instead, if we take the opposite of x plus 1, and obviously we get the same interpretation as the last example. In the end, we get x equals -2 as our solution, and x equals +2 as our extraneous solution in the same way. So so that's what I would have to say about that second way of interpreting it. Both are great. Math works.
Yes, indeed. All right, and that completes the discussion around exam item 33. We hope that you're finding that helpful, and stay tuned for the next item.